Hi guys, Mrs. Delisin here. Welcome to another lesson of AP Statistics. Today's lesson is significance test for one proportion. Can you taste the rainbow? Many students claim that they can taste the different colors of Skittles. By the way, there are 5 colors in the Skittles bag. Today we will conduct an experiment that perform a significance test to see if students really can taste the rainbow. So our goal today is to see if the group of students that we are going to look at can taste the rainbow or can tell what flavor even without looking. Okay? So how many correct and how many total? So I'm going to be using last year's because of course we can't do it because you're not here with me. I'm using last year's data. We tested 150 Skittles and 97 of those Skittles were that they guessed correctly. And so our statistic, which is our sample proportion, would be 97 over 150. What is that one? 647. 64.7%. Okay, there you go. Our significance level is 5%. We're also going to be doing, you know how we did it on the confidence interval? We have state, plan, do, and conclude. We're doing the same. We'll start with our parameter. So for our parameter, we are going to guess the true proportion. That's our goal, yeah, to know the true proportion of correct guesses for all Skittles. Okay, and as I have mentioned earlier, there is only 5 colors of the Skittles. So if you're only purely guessing, right, there's a 20% chance that you will get it right. Like when you're doing multiple choice. If the multiple choice is A, B, C, D, E, and you don't know the answer, right, there's 20% chance of you getting it correct purely by chance. So our null hypothesis, H sub O, is going to be P is 0.20. And our proportion here, our sample proportion is 64%. So we are saying that the alternative is not 20% but greater than it. Okay? And name of the procedure, this is another one that is new. It's called one sample. Because of course, we only have one sample. Z-test for P. Please take note that when we did chapter 8, the confidence interval, the name was one sample Z interval. Okay, but this one is one sample Z test because we are trying to test if this group of students can really taste the rainbow or can taste the Skittles. Of course, we're going to be checking condition, which is the same thing. We need to know if it's a random sample. So yes, it is a random sample of Skittles. And then 10% condition. 150 is less than of all Skittles in the bag. And then we need to check NP or large count. 150 times 0.20. That's 30. And then 150 times 0.80, that is 120. Okay? And both of these are greater than or equal to 10. And please note, I want to make sure that you guys are understanding the difference in here. In confidence interval, right? Because we have 2 P's in here. I have a P equals 0.20 and I also have a P equals 0.647, right? A P hat and a P. For checking the condition, for the large count condition, we don't use the P hat. We don't use the sample proportion. We use the P, okay? We use the null. So let me put that one in here. The formula is n times p and n1 minus p, not n times p hat. Okay, there is a difference. You don't do 150 times 0.647. You see this one? You don't multiply this by 150. You multiply the null by 150. Okay, but miss, why am I using n times p hat in the confidence interval? Because in the confidence interval, you do not have the p. You are not given the p. You are trying to estimate the p. And that's the reason why you're going to use p hat when you do your large count. Okay, I hope that is making sense. Our general formula is, of course, the z-score, or z equals statistic minus parameter divide by SD. And our specific formula would be z equals p hat minus p over p1 minus p over n. Please take note, I am use p, not p hat in the bottom. Okay, and miss, why do I use p hat on confidence interval? Again, you use p hat because you don't have the p. All right, and so I'm going to do z equals, let's plug that in, 0.647 minus 0.20 over 0.20 times 0.80 divided by 150. And this is z equals 13.68. Really, really, really big z. So the percentage is going to be really, really small. Okay. And at the same time, let us draw our picture. So our n is 0.20. Our standard deviation, I know I did a shortcut on the standard deviation, but the standard deviation part is this one. But you can put all of this all at once in the calculator, that's why, so it's easier. So I can put, just to make sure you know, let's put that in there. Okay? And of course, you don't have to put that. I just want to put the formula because I want you to know where I got it. So this is 0.20 and 0.645 is going to be around this area. Or I think really small. There. Okay. So we have our test statistics is called the z-score. That's 13.68. And our p-value is the area to the right of it. The area to the right. If we look at the table and we use the table for the z-score, we don't have 13.68, right? Because this is a really big z-score. We can use our calculator, but we do know that this number is going to be really small. So this one, actually, that is not accurate. It has to be like smaller than that. But I just want to show that it's on the right side. Our p-value is going to be approximately 0. Okay, approximately 0%. So that's it. And then we make our conclusion over here based on our p-value. And let me go back quickly, and based on our significance level. First, we have to interpret. Remember on the previous lesson, you interpret the p-value and then you make the decision based on your p-value. So let us use our p-value first to interpret. And remember, you always start with the word assuming. Assuming HO is true, our HO is p.20. There is an approximately 0, right? Probability of getting, I know it's a lot of writing, of getting a p hat of 0.647 or greater purely by chance. And we are going to make our decision because 0 is way less than 0.05. 0.05, by the way, is our given alpha. We reject HO. We reject the null hypothesis, or we going against the null hypothesis. We reject the null hypothesis, and we do have convincing evidence that this class, right, the students in this class can taste the rainbow. Okay, that our P is greater than 0.20. So in this case, I'm going back to my hypothesis here. If the p-value is greater than 5%, I believe my null hypothesis. If my p-value is less than 5%, I believe my alternative hypothesis, because I have a convincing evidence to go against my null, technically. All right, good. So let's do our important idea section. What did we learn? We need to make sure that we do state, plan, do, and conclude. And formula for one sample z-test for P. Let's put the formula here. We have standardized test for statistic, or technically that's just a z-score, equals statistic, or the sample proportion, minus the parameter, that's the mean, equals the SD. So this is Z equals P hat minus P over, please take note, we are using P at the bottom, not P hat. Okay, we're good. And I would also want to introduce you to something. Now that we had a P hat, let me go back to my P hat. P hat is 0 in here. And if you remember when I was in the previous lesson, for alternative hypothesis, that could be P is greater than a number, P is less than a number, and sometimes you are unsure if it's less than or greater than the claim. So that's when you use a not equal symbol. Oh, sorry, right here. All right, not equal symbol. So if you say, the probability of, or let's go back to the shoppers of bananas. There are 75, according to the manager, 75% of the people who goes to the grocery store buys banana, right? And if you're unsure if it was greater than 75%, if the true percentage is greater than 75 or less than 75, you can use the not equal symbol. And I'm going to be showing you in the check understanding portion how that goes, okay? And then I would like you to also remember that this is called a two-sided. Two-sided means you're unsure if it's greater than or less than. It's both, right? And when that happens, you multiply the p-value, your result, your area, you multiply the p-value by 2. Okay, let's see how that works. Let's have an example. Sometimes parents and grandparents like to recount how difficult life was when they were kids, such as having to walk 10 miles to school in the snow, uphill both ways, or you see You hear you guys parents say that all the time, right? No, when I was a kid, I don't even have that. I don't even have this, right? A random sample of 180 teenagers were selected, and 40% had heard stories from their parents or grandparents about how difficult life was when they were kids. Do these data provide convincing evidence at an alpha level of 0.05 or 5% that the proportion of all teenagers who have heard stories from their parents or grandparents about how difficult life was when they were kids differ from 0.50? Okay, and I would like you guys to highlight the word differ. When you say differ, right, technically it's different from. We don't know if it's greater than 50% or lower than 50%. What we have here is that we don't know. So this is what we call the two-sided what? Either it's below or above. We're just sure that it's different from the proportion that we have. Okay, let's do our parameter. So P is the true proportion of all teens who have heard stories from their grandparents. And I don't have space for my hypothesis. Let's put that in here. My hypothesis HO is P equals 0.50 because that's the claim. My alternative would be P is differ or not equal to 0.50. Okay. Statistic is out of how many teenagers? Out of 180 teenagers, 40%. So I don't even have to solve it because I was given that it is 40%. I know it's lower than 50% at this point, right? And our significance level is given 0.05. Name of the procedure, 1 sample z-test 4P. Remember, we're not doing an interval, we're doing a testing. We want to test if the proportion of all teenagers who have heard stories is different from 0.50. Check your condition. It says a random sample of 180. So it was a random. Why do we check random sample? We check if it's random so we can generalize it to the population. Random sample of 180 teens. Next, 10%. 180 is less than, right? This is kind of obvious, yeah? 180 is less than or not even equal, is less than a tenth of millions of teenagers around US. Teenagers, there. And then large count, it's n times p, not n times p hat, okay? N times p. So that is going to be 180 times 0.50, not 40, not 0.40. And that is 180 times 50 again. And that is 90. That is 90. Both are greater than or equal to 10. So the sampling distribution of p hat is approximately normal. There you go. Our general formula, I'm not going to put the general formula anymore, okay? Because it's already on the check understanding portion. I'm just going to put my specific formula. Z equals p hat minus p over p1 minus p over n. And that is z equals 0.40 minus 0.50 square root of 0.50 over 180. And our z here, again, a number that is really, really big. When I say big, it's a big z-score. Okay, so which is 2.68. And then remember that when you go to, if you go to, you're not going to get an accurate number if you go to the table, because the table will only give you an approximation, yeah? So at this point, I am going to urge you to go to your calculator. And to do that, all you have to do is you go to Menu, Distribution, and then on the lower bound, you're going to put negative 1,000. On the upper bound, you're going to get negative 2.68. And then keep your mean and your standard deviation 0 and 1. And you will get, let me write that down here. Normal CDF, your negative 1,000, negative 2.68, 0, 1. And you are going to get 0.0036. And remember, because this is two-sided, I am going to multiply my area into 2, which is 0.0072. And that is the p-value. And why did I multiply it by 2? Because my alternative hypothesis is a not equal symbol. Now, how does that look, right? How does that look in a picture? So let's draw our picture so we have more idea on what do you mean by two-sided. Okay, two-sided here, this is my point 50. Point 50 is my mean, okay, my parameter. And then the 40% is both at this side, because I don't know if it's, you see how 40% over here? There. For less or more, so that is two-sided. So I have that both 0.40 and 0.40 on both sides, right? And I want to get the area of this, which is this 0.0036, and I'm going to multiply that by 2 because I also want that area in there. Does that make sense? Hopefully. So that's it, you guys. And then we are going to make our conclusion. Let us make conclusion. First, let us do an interpretation of our p-value. Assuming, we always start with that word. Assuming HO is true, HO is null hypothesis, that it is 50%, there is a 0.072 probability of getting a p-hat of 0.40 or lower, or 0.60 or higher, two-sided, remember, purely by chance. So you see this? You see this? This is 0.40 or lower, or 0.40 or higher. So what's the probability of getting either on both sides of 0.40? Okay, purely by chance. And then, because, this is our conclusion part, because 0.0072 is less than 0.05, we reject the null hypothesis. We reject that HO is 0.50. And we do have, I wish we have an example that is we do not have convincing, yeah? And we do have convincing evidence that the true proportion of teenagers who have here stories. I know it's too much writing. Differs. Let me make that bigger. Differ from 0.50. So again, I'm not saying that it was less than 50%. I'm not saying it's greater than percent. What I'm saying is that the true proportion is not equal to 50%, regardless of if it's more than or greater than. Oh, sorry, more than or less than. Okay. A 95% confidence interval related to chapter 8 for the proportion of all teenagers who have heard stories from their parents or grandparents about how difficult life was when they were kids is in between the interval 0.32 and 0.47. Explain how the confidence interval is consistent with but gives us more information than the test. Okay, it's consistent because now remember that it says that our P parameter, our claim is that it's 50%, or sorry, their claim is that it's 50%. Now, if we look at our confidence interval, the 50% is not in it. It's not within, right? Both of our upper and lower limit, they're both below 50%. So, let us try to do this. The null hypothesis value, or I could even call that my parameter, 0.50, is not contained in the confidence interval. So we would reject HO. The interval also gives other plausible values for the true proportion. Okay. I hope this is making sense. And let me clarify. Remember when we did the z-test, right? It showed us a convincing evidence that it is not 50%. It's above 50% or below 50%. In the z-test, we don't know. We don't have that information if it's above or below. What we just know is that it's not 50%. It is not equal to 50%. But our confidence interval tells us that it is not for 50%, but it's lower than 50%. And that is how, you know how the part says, explain how the confidence interval is consistent with, but gives us more information than the test. It gives us more information because it shows that it is less than 50%. Unlike the z-test, that we're unsure if it's on both sides of, it's either above or below 50%. Okay? All right, that's it, you guys. I hope that this lesson is giving you more information on how to make conclusions about testing, and hopefully you can do it on your own during the test or on your homework. Thank you. I will see you guys on the next video.